definition is the geostrophic wind. And so what I've done is I've taken this to the other side. So I've got Fk cross UH minus UG. Voila, that's what I have there. All right. The second equation that I have written down is thermal wind. I'm going to derive that in a second, just because it's so important to our discussion. This is the thermodynamic equation. That's an expression d by dt of the potential temperature is 0. Oh, sorry, yes.
Just wondering if you could clarify what you mean by the little up hat in the equation?
What I mean by the what, sorry?
The character you give when you get shifted 6, I don't know exactly.
Oh, sorry, yes. All right. There are two ways of writing cross product, two symbols. One symbol is this, A cross B. The other symbol is that, A cross B. It's a cross product. And K is the unit vector in the vertical. In fluid mechanics, you both get used. And I've used the caret. You'll see throughout this whole lecture that the caret is cross product. Yes. Thanks. Yeah, so this is conservation of potential temperature. It's really an expression of first law of thermodynamics. But like Michael, I've written the thermodynamic equation in terms of this thing called, we sometimes use the word buoyancy, but maybe the system buoyancy is better. It's a scaled version. Theta star is a constant, so just some, and then it's a theta perturbation, a deviation from some background state. But really, I don't have to do that. I just have, partly because Michael's done that, partly because that just makes some of the mathematics a bit neater. But that's the first law. It's saying that if we vect B by the geostrophic wind, that's the quasi-geostrophic approximation. This is the advection by the geostrophic wind there. And then we've got the vertical advection, not of B, but of the background static stability. And this is the continuity equation. In the continuity equation, I've used a property that I'll use a few times, and that is that the divergence of the geostrophic wind is 0. We say that the geostrophic wind is non-divergent. If you haven't seen that, or you've forgotten it, perhaps you should show it as an exercise. Show that. Now, I'm going to just derive that, because sometimes thermal wind looks like it's a bit mysterious, but it's kind of simple. It's geostrophic balance and hydrostatic balance. That's it. There's nothing. And also, if I derive it, it'll just reinforce some of these symbols. So let me do that. So what's the expression for the geostrophic wind? The expression for the geostrophic wind is Fk cross U equals 1 over rho grad H P. So what I'm saying here is that the Coriolis force balances the pressure, there's a minus there, pressure gradient force per unit mass. Pressure gradient force per unit mass. And if when they balance, we put a little subscript G in there to say that's the definition of the geostrophic wind. And we can rearrange it. We can take K cross both sides. So we can K cross, that changes the sign. So FUG equals 1 over rho K cross grad H of P. I'm going to assume that the density is a constant just because it makes life easier and simplifies the mathematics. So that's the definition of geostrophic wind. Hydrostatic balance. Whoops. hydrostatic balance, Michael wrote this down, and that is 1 over rho d by dz of P equals B. If I differentiate this with respect to Z, I get F du G dz equals K cross, I'm going to put the rho inside because it's a constant, d by dz 1 over rho P. What's that? It's B. That's a vector. So it's a consequence of two things. Rossby number being small, giving us geostrophic balance, and hydrostatic balance. That's the end of the story. Now, if the Rossby number is small and it stays small, so in other words, we're talking about a weather system. If the Rossby number is small and it stays small, then the thermal wind balance must be maintained. So this has to be true for all time if the Rossby number is small. Now, let's come back to the possibility that the Rossby number changes later on. Let's don't worry about that for the moment. So, although the vertical motion is not explicitly predicted in the quasi-geostrophic theory, it's implicit. It's got to be there. You can't just ignore it. And we're going to derive an expression for that vertical motion. And it's called the omega equation. It's called the omega equation because this is usually done in pressure coordinates, and vertical motion in pressure coordinates is omega. But I'm going to do it in height coordinates, as many people do, and still call it the omega equation because it's a bit more, recognisable than the W equation. And what we're going to do is we're going to write an equation for the rate of change of the thermal wind. And that is fundamentally it. Fundamentally, we're going to see that we get vertical motion because the vertical motion is needed to maintain the thermal wind balance. That's the physical reason. So whenever you change temperature gradients, there must be a vertical motion that goes along with it.
This d by dt sub g,
Yeah.
Is that just reminding us that we're in quasi-geostrophic balance?
Yeah. It's reminding us that we're doing the advection by the geostrophic wind. So d by dt subscript g is to remind us that the material derivative is calculated using the geostrophic wind, not the actual wind. Yeah. So there are sort of two bits to the quasi-geostrophic approximation. One, the momentum, UG, is approximated by its geostrophic value, and all advection is done by its geostrophic value, and that's to remind us of that. So you can see the strategy here. The strategy is go back to the equations of motion. There we are. Derive an equation for d by dt of the vertical shear, d by dz of ug. Derive an equation for the horizontal gradient of the buoyancy, or the potential temperature. Use that to bind them together. All right, I'm going to do one bit of the problem mathematically, and then I'll put then the mathematics I will leave on the slides but not do, but because I'm guessing you will get given the slides and you can work through them yourself later on. But let me show you the strategy here. So the thermal wind equation is a vector, and remember what was it? It was F vector UG dz, that's the horizontal wind, is equal to K cross the horizontal buoyancy gradient. Let's write it in component form. The two components are dug dz, dvg dz. They're the two components of that first vector, and the components of the second vector are these. Do you remember how to do cross products? I had to think back to your first year calculus. as an exercise, I think you might want to just show that that second line are the two components of that vector. So what I'm going to show you is that the equation for d by dt of this equals something called q, which Michael's introduced, plus something, an ageostrophic wind. D by dt of B, buoyancy gradient, is q and a vertical motion. And let me also say that my notation here is VGZ is d by dz of Vg. So that subscript V means differentiation with respect to Z. That subscript X means differentiation with respect to X. Just makes things a little more compact. So what I want to do is I want to derive that first equation, and then I'm not going to do any more derivations explicitly. I'm just going to step through the recipe. So what I want to do is I want to show where that comes from. So let's do that. All right, let's write down the V momentum equation. D by dt of Vg plus UA equals 0. Oops, let me not a vector. That's the first component of the momentum equation. Let's differentiate this with respect to Z. And remember that big D by dt is this. It's got a product in it. So you can't interchange a partial derivative with a big D. So we're going to differentiate with respect to Z and multiply by F, the Coriolis parameter. And now, how did I get that line here? When I differentiate this with respect to Z, I'm differentiating this with respect to Z, and there's a product here. So I have to remember the product rule? The product rule is I would differentiate this and leave that bit alone, leave that alone, and then differentiate this. Product rule. And that is what I get. This thing here is this Q1. Let's expand that out. So let's take that dot product. That's du g dz times dvg dx plus f times dvg dz times dvg dy. See what I've done here? That has two components. D by dz of ug, first component. Second component, d by dz of vg. There's the first component, there's the second component. Dotted with grad of vg. First component of grad, second component of grad. Then I'm going to use two things. I'm going to use the components of the thermal wind equation So I'm going to, where I see that, I'm going to replace it by a buoyancy gradient. Where I see that, I'm going to replace it by a buoyancy gradient. And here, I'm going to use the result that du g dx equals minus dv g dy. Do that, dot, 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 and we get this expression. D by dt of the shear of the V component of the wind is Q1, where Q1 is that, and then there's this other term. All right, what's the big deal? Well, here's the big deal. The big deal is that if I do the same for the buoyancy equation, I get the following. d by dt of the buoyancy equals plus q1, whereas this has a minus q1. So what's happening here? Q1 is something involving geostrophic winds and potential temperatures. It's related to the background flow, the geostrophic wind and the buoyancy. And yet, Q1 is, let's suppose Q1 is positive. Q1, if there was no vertical motion, would increase the buoyancy gradient. At the same time, well, that was stupid. Q1 increases the buoyancy gradient if there's no vertical motion, but Q1 decreases the shear. But that can't be. You can't push the thermal wind equation in one direction while simultaneously pushing it in the other direction and maintaining thermal wind balance. So the vertical motion and the ageostrophic wind has to come to the rescue. The vertical circulation is what binds the thermal wind equation together. One ring to rule them all. So what we do now is we subtract one from the other, and then we have an equation. So that minus that must be 0. d by dt of the thermal wind is 0. If I take that minus that, these add together to give us a 2 times Q1. And that's what we get there. And I'm going to call this equation 1. I've lost track of the time. Where's it? Okay. I see it. There's a clock here. The clock there is somehow turned itself off.
It's about 12:15.
Okay. All right. I'm not going to go through it again, but we could just go. We do this. This is the recipe. Do the same again for the other component, and get another equation. You do that. There it is. And I call that equation 2. Add equation 1 and 2 together. It gives us this. And now we have a vector. We have a Q1, which comes from the first calculation I did, and a Q2, which comes from so one from the x direction and one from the y direction. This is the Q vector. Do some manipulation, and voila, this is called the omega equation. I could have written an equation for the divergence if I wanted to as well. You know, so what I mean is, we talked about vertical motion and upper divergence, and how upper divergence isn't really an explanation for vertical motion. The same equation, almost the same equation, d by dz of that equation gives us the upper divergence. So they just go hand in hand. You got one, you got the other. All right. The omega equation, this is it. So what does it look like? This is the static stability squared, the horizontal Laplacian of W, the vertical motion, the Brunt-Feister frequency squared, the vertical derivative of the vertical motion is equal to 2 times the divergence of this Q vector. There should be a negative correlation between this and this. Do you know why? Maybe think about that. Now I could solve that equation, we could do some more mathematics, and we could solve that perfectly well. Right? It's an elliptic equation. I could make it look like Poisson's equation. And maybe you know how to solve it, maybe you don't. We can go ahead and do it. I could do it, but I don't want to do it and don't need to do it. The models are perfectly good, are perfectly okay at giving us, predicting the vertical motion. This is about understanding. So how could I use this to help me understand the dynamics of weather systems? Not go and make a forecast of W or work out all the details, just understand why and where I should get vertical motion. Well, I've said I don't want to solve it, but I want to draw an analogy. And the analogy is a trampoline. Suppose I stand on a trampoline. Here I am standing on a trampoline. What happens? The surface of the trampoline deforms. The component of the tension in the trampoline that way balances the weight force that way. I'll draw a trampoline. Now, this is where you should turn off the videoing, right? Because, all right, so here, this is the surface of the trampoline. Here I am, standing on the trampoline, and if I could draw it in 3 dimensions, you know, it'll look, oh, well, you know, something like that, all right? But the point is, I've deformed the trampoline. The equation for the displacement, you may not know this, is the Laplacian of the displacement equals minus the force per unit area. So here we go. We know what the solution of Poisson's equation is. It's, if I poke it here, it deforms, but it doesn't just, the response is not just local, it spreads out. Right. That's all we need to know. That's good enough. That's the 2-dimensional Poisson equation. In 3 dimensions, it's like Michael's PV ball. Action at a distance. All right, that's good enough for the moment. Except to notice that there's a minus sign there. And the minus sign's there because if I poke the trampoline, I push in that direction, I want the displacement to be in that direction. And if without a minus sign there, the displacement would be the opposite direction to the force. Have a think about why that might be. All right, so I want to think about how I could calculate the Q vector and use it without doing any complicated calculations, without solving this Poisson equation, without, well, I won't say without doing many mathematics, do a little bit of mathematics, but like the PV approach, we want some principles that we can apply to observations or models and be perfectly confident without doing any calculations that this is the way the world's going to work. That's one of the really great strengths of the PV approach, and that's the kind of what I'm trying to build here. This, where should we expect upward motion and downward motion in weather systems without doing calculations? So, this is the Q vector that we've just derived. It has 2 components, and I derived just a tiny fraction of that. So, pardon me, this is minus the x derivative of the zonal geostrophic wind, the x derivative of the buoyancy minus etc., etc. So I just wanted to remind you of the notation. That's UGX is the same thing. Now in the omega equation, where are we? The forcing, the right-hand side, is the divergence of Q. Divergence of Q. So if we had a distribution of Q, if I knew what Q was, say it was just this localised vector, then it would be convergent on this side and divergent on that side. There's my vector. Here it is. Here's a perfectly good vector. 0 out here, 0 out here, convergence on this side. Not convergence and divergence of mass, convergence and divergence of Q, this vector. So we might expect upward motion where we had convergence of Q and downward motion where we had the divergence of Q. Now, so Q points towards regions of ascent and away from regions of descent. Here's an example. This is an example of a cold front, and everything I'm going to do is in the northern hemisphere for two reasons. One, I don't have to think about F being negative, which sort of complicates the signs, and two, because you can go away and do it. All the examples I now do, go away and do them for the southern hemisphere. Right? See how they work. Now on the left-hand side, the left-hand panel here is the potential temperature at 700 millibars and the wind field. And on the right-hand side, it's the temperature at 700 millibars and the Q vectors. And I'm hoping that you recognise a cold front through here. These solid lines are isentropes, lines of constant potential temperature, or lines of constant B. Same thing. And here's the cold front through there. There's the warm front back there. You can see the, maybe I'll draw the, I better be careful here because Michael's told us what cold fronts are not. I'm hoping that this is, and there's the warm front at the back of it. Here's the low. Here's the Q vectors. So some computer program has gone through and calculated the Q vectors. We're going to, in a few moments, think about how we might do that without the aid of a computer program. But let's highlight one or two of these Q vectors. There's the Q vectors. They're large there, and they're effectively zero out there. In other words, I would anticipate rising motion through here, and I'd anticipate sinking motion through there. Rising motion ahead of the front, sinking motion behind. That's not a big surprise. Now, before we start guessing what Q vectors look like, I want to do one other little calculation. So, how can I estimate qualitatively the vertical motion using Q vectors? Well, remember, this complicated expression here involves derivatives in the x direction and derivatives in the y direction. But let's change our coordinate. Let's rotate our coordinate system. I haven't really, x can be any direction we like, and y has just got to be orthogonal to it. So let's change our coordinate system. Let's at each point rotate our coordinate system. So let's say that was x, and let's say that was y. So there's my coordinate system. But now let's align x with the buoyancy, with the isentrope. So say the isentrope is pointing that way. Let's go like that. There's my new coordinate system. I can do that. It's completely arbitrary where I point x. But when I do it, let's relabel it. Let's call that S and let's call that N. So just to remind myself that's what I've done. And I'm going to, so here's the isentrope, B equals a constant. This is the y direction, there's the x direction. And I'm going to choose my N to point towards the cold side and S to point along the isentrope. So all I'm going to do is where I see an X, I'm going to make it an S. S, S, S. Where I see a Y, I'm going to make it an N. N, 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 N. And now, because this coordinate system points along the isentrope, d by ds of b, as I walk along that isentrope, it's always the same. So if I differentiate along that isentrope, it's 0. So d by ds's of the b's, get rid of them. And what you'll find, and I'll leave this as an exercise for you to do, show that you get this. And show in vector form, it's that. All right, so there's about 2 lines of algebra. When I say show this, all these exercises I've given you, they're like 2 lines of algebra when I say show this, show that. Right? So what physically does this tell us? Physically, Q is equal to the magnitude of the buoyancy gradient. So are the isentropes packed close together or are they far apart? K cross the derivative, the change in UG along the isentrope. So do you remember your right-hand rule? So this physically is, how is the geostrophic wind changing as I walk along an isentrope? So here's an isentrope. It's a B equals constant. I walk along it. I measure the vector UG here. I walk a bit further. And I measure UG. And I take that minus that, divide by the distance I've just walked. That's it. That's what that derivative means. So this is, whoops, GU, G, ds. And this is K. Vector K cross, right-hand rule. K, du, G, ds, K cross, right-hand rule, something in that direction. But there's a minus sign here. So that's K cross U, G, ds. But of course there's a minus sign. It's out this way. So the Q vector can qualitatively be calculated by working out how the geostrophic wind changes along the isentrope and the rotating clockwise through 90 degrees. Let me do an example to show you that this is not as hard as it sounds. This is an example that Steve talked about yesterday. It's the vertical motion in the jet exit. So what do I mean? This is a really typical synoptic weather pattern. So these are the isentropes. They could be theta, they could be temperature, they could be B that I've used, it could be even thickness. Cold on this side, warm on that side. This is the pressure or the streamlines. So what this says is that where the streamlines are close together, then the wind field, UG, must be large. Where the streamlines or the pressure or the isobars are far apart, UG must be small. So what we do now is, so what's our formula? Our formula is to work out the change in the geostrophic wind as we walk along the isentrope, and then rotate clockwise 90 degrees. So first thing, let's work out that change. Where are we? It's this minus that. So that's a vector in the opposite direction. That's the black vector here. This thing here. The wind upstream minus the wind downstream. So it's something which is small minus something which is large. This is the change. So this is the change in UGDS. Rotate through 90 degrees. Gives us this. So rotate this thing clockwise. It gives us that. That's the Q vector. We get upward motion. We get upward motion here, and we get downward motion there. Let me say it again. I've put this the wrong way around. The Q vector points towards upward motion. So I'll do that. So in this situation, at the exit of the jet, on the cold side, we have upward motion. On the warm side, we have downward motion. Why don't you do this for the jet entrance? Now this is absolutely one of the prime spots for severe weather. When you're looking at the charts as part of your project, look at the jet exit region and look on the cold side of the jet exit That's where you've got rising motion, you're advecting upwards cold air, and very often you'll see the most severe weather there. Forecasters also look for where you have the jet exit on the cold side overlapping with the jet entrance from the next jet. So you get this doubly upward motion. All right, so that's one of those things you should be looking for in your charts. Next one, Rossby waves. Where would I expect the vertical motion? This is rhetorical. Where would I expect the vertical motion in a Rossby wave? So here I have a sequence of highs and lows. Well, let's use our rule. The Q vector is calculated as the change in UG along an isentrope rotated clockwise through 90 degrees. So now these solid arrows are the Q vectors. And I'm going to just draw them here then to tell you how I got them. So the Q vectors point towards ascent, so there should be upward motion there, and there should be downward motion there. There should be upward motion ahead of the low and behind the high. Now, how did I get that? Well, let's think about the following. These dashed lines are the isotherms, and around the low, again we're in the northern hemisphere, remember, so around the low, the flow in the northern hemisphere is like that, anti-clockwise. So we have motion in that direction around the low, and on the other side of the low, we've got motion like this. So southerlies ahead, northerlies behind. Here around the low we'd have northerlies ahead, southerlies behind. So these are the streamlines. What do we have to do again? We have to walk along the isentrope, here it is here, with cold air on our left, so that's the direction S points, and we have to take this minus this, which gives us something which is like that. That's it. So that minus that is this. So I'm doing a finite difference. Rotate clockwise is that. Voila. So when you see a Rossby wave propagating, expect rising motion at the leading edge of the trough. You probably already noticed that on the charts already, but there's the theoretical underpinning for that. I'll do one more example. This is a bit more frontal-like. So this is an example where are we? These are the isentropes, the dashed lines. This is the cold side, this is the warm side. As advertised, every one of these examples have been Northern Hemisphere. I want you to have a go at these yourself for the Southern Hemisphere. So we've got these. So this is these solid lines are the streamlines. So we've got northerly. Let me say it again. Southerlies here and northerlies on the other side. Go to the same argument. Actually, I might just leave this as an exercise for you to fill in. Calculate the change in the velocity along one of these isentropes. Show that there's the Q vector is large here and it's small out there, and this is the vertical motion. Actually, in this particular example, this really is omega, which is dP by dt. So W is the negative of that. How does this work in the Southern Hemisphere? I'm going to leave that for you to think about that. Why does it? You use the same rule. Walk along the isentrope, calculate the change in the velocity, rotate through 90 degrees. That's the Q vector. Why does that work in the Southern Hemisphere?
So it's clockwise in both hemispheres?
Oh, actually, that was a rhetorical question, actually. But sorry, what's your answer?
No, my question was, is it that you rotate clockwise in both
Yeah, you do. Yeah, you do. Yeah. Normally it's rotate the other way, isn't it, when you change hemispheres, but somehow this seems to be working out for both hemispheres. Here's another exercise for you. So Michael talked about the PV ball and talked about vertical motion associated with an isolated PV ball. Do this from a Q vector perspective. Work out where the vertical motion should be and why from our Q vector rules. Oh, I don't want to show that. I want to just leave you with one other thing. The Q vector form of the omega equation is sort of the modern form of the omega equation. The omega equation was derived 100 years ago, or something like that. And there are generalisations of the Q vector, of the omega equation as well. It was originally derived in this form. It had two terms. One is the vertical derivative of the advection of the relative vorticity, and the other one is the Laplacian of the thermal advection. And for a very long time, this has been the preferred form used by forecasters. And the Laplacian of the thermal advection is kind of thought to be the forcing at low levels, and the differential vorticity advection is thought to be kind of the forcing at upper levels. You can mathematically that right-hand side is the divergence of Q, 2 times the divergence of Q. But the divergence of Q is a much neater way to do this calculation. First of all, it's a divergence of a vector. And secondly, these two terms, the differential vorticity advection and the Laplacian of the thermal advection, are about the same sizes of each other and opposite. So you've got the difference of two large terms. So you run the risk of lots of internal cancellation. On the other hand, it's mathematically correct, but I sort of hesitate at using this form because of this large internal cancellation. But it's still used. Let me finish with one last thing. These patterns of vertical motion and the implications and deductions that we make from the omega equation are entrenched in the way we think about weather. We even use them in the subtropics, these same ideas, and to some degree in the tropics. Quantitatively, they don't work because the Rossby number is not small, but qualitatively they do. And the generalisations of the omega equation to larger Rossby numbers are more complicated and more accurate, but they fundamentally give the same kind of pattern. Perhaps I'll stop there. Thanks.